Hello, grade 12s, and today we're going to start our study of quantum theory, taking a look at another model of the atom. But I want to do that by going back a little bit in time and taking a look at what we considered atoms to be historically and some of the things that we've taught you in the past. Now, up until about 1900, people thought of the atom as being this hard, indestructible mass. It was almost like you could picture in your mind a metal ball bearing. And there was an image of a very small version of this that could never be destroyed. But after around that time, a gentleman by the name of J.J. Thompson revised the model, and he came up with something called the plum pudding model of the atom. Now, the plum pudding model for the atom talked about, for the first time, electrons. And electrons were these little negative bits that were floating around inside this jelly-like mass of positive. And he thought of it like plum pudding, which is kind of like a bowl of porridge, that the porridge part would be the positiveness and the raisins would be the electrons. And so this was the image he had in his mind when he came up with his model. Thompson came up with this idea by doing a very famous experiment called the cathode ray tube experiment. So this is something that we should associate with the work of J.J. Thompson. And what he did was he connected a high voltage source to a vacuum tube called a cathode ray tube, and it sent this beam of, to him, light energy. You can see this beam of light going through the tube when he got the voltage going. And what he found very interesting was that if he subjected this stream of light to an electric field, it was attracted to the positive side of the field. And so he defined this beam of light as being electrons. And we know that positives are attracted to negatives, which is why the field bent upwards towards the positive field. And he named this the electron and decided that electrons had to be a negative charge. So this was a really famous experiment done by J.J. Thompson. You can read a little bit more about his experiment on page 109 of your textbook. Following Thompson, we had a further refined model done because of Rutherford. Now, Rutherford came up with the idea that the protons, the positive, wasn't just the jelly. In fact, it was all contained in the middle in something called the nucleus. And the word nucleus literally means the middle. And he decided that all of the positive energy would be stuck there in the middle of an atom, right there. And he did this by doing another very, very famous experiment in chemistry called the gold foil experiment. So what he did was he took a source of alpha particles, here's the letter alpha, and basically these alpha particles from this radioactive source were shot through some gold foil. Now, the thing about gold is that it is a very malleable metal. You can pound it out very thin. In fact, you can pound out gold sheets to being only 1 or 2 atoms thick. And these alpha particles are essentially positively charged. And he surrounded it by a screen of a type of photography paper. And so what happened was, when he shot his stream through the gold foil, for the most part, the particles would hit the photography paper and make a little black dot on the paper. And there was a little bit of diffraction. He saw that there was a few places where it shot through, and he thought, well, okay, this kind of makes some sense. But what really struck him as being interesting was every once in a while, one of those particles would hit the gold foil and then go winging off. Can you imagine a large black box with a shape underneath it, and you have to shoot bullets at it? And based on the way the bullets bounce, decide if that's the shape of the object. It would be an interesting and not very safe experiment to do, especially if every once in a while that object were able to bounce the bullet right back at you. Rutherford had a similar thought in his head. What could possibly be powerful enough to bounce this alpha particle right back at me? What he decided was, most of the particle of an atom was empty space. And in that empty space, there was electrons. He never said what the electrons were doing. They were just in that empty space. But in the center, in the nucleus, was a very small and very dense positive charge. And that what happened was when an electron hit that central nucleus, it caused, or sorry, when an alpha particle hit the central nucleus, it caused it to come bouncing back. And so this completely reformed what we thought of as an atom. Now, in and around grade 9 and 10, we started doing Bohr diagrams, and Bohr's a really interesting scientist. Bohr's model actually said where the electrons were. Bohr decided that electrons didn't just rotate willy-nilly around the nucleus, but actually had fixed orbits. He pictured it kind of like orbits rotating around the planets rotating around the sun. And he decided that these electrons existed in these orbits. He did this by studying hydrogen and subjecting hydrogen to electricity in a vacuum tube and realizing that it was glowing a very distinct color, and he correlated the color of light energy that was given off to a specific wavelength. Every color of light is a specific wavelength. You can read more about this on page 146 of your textbook. So it was a really interesting experiment. The thing that was truly fascinating about it was the math that he applied to his theory worked out absolutely perfectly for hydrogen. In fact, it was so simple and so perfect that people really had a hard time trying to argue with what he was talking about. It was simple and elegant. The problem with Bohr's theory is that the math stops working the bigger the atom gets. It doesn't go 100% off, but you start having to apply modifiers. Now, we're not going to get into calculating the math behind his theory in grade 12 chemistry, but suffice it to say that the formulas are reasonably simple. So Bohr wasn't entirely wrong in his theory. He just was overly simplistic about it. There are a variety of different scientists who have expanded on Bohr's theory, and now we talk about a quantum model of the atom. The biggest difference between a quantum model of an atom and Bohr's model is that the quantum model is a mathematical model, and it's based on probability. Okay, it talks about where an electron probably is most of the time. This contrasts with Bohr, who talked about where an electron will be found all of the time. So where is the electron probably most of the time, and where is it found all of the time is the biggest difference. So before I go into explaining how we describe atoms in the quantum model, I want to take a moment to go back and review a little bit about grade 10 and grade 9 when we talked about Bohr model. You might remember from grade 10 and 11, we know that if I wanted to draw the Bohr model for a particular atom, that I would use a couple of different indicators. So suppose I wanted to draw the Bohr model for aluminum. Because aluminum is in the third period, period 1 starting with hydrogen, period 2, and period 3 is the one that starts with sodium, magnesium, and goes all the way across. Because aluminum's in the third period, I would draw it by using 3 rings. I'll put the symbol for aluminum, and then I will draw 3 rings for 3 periods. I know that aluminum will need a total of 13 electrons because it's at atomic number 13, and I will expect that aluminum will have 3 electrons in its outer ring, its valence ring, because if I number my family, skipping my transition metals, I find it in family 3 on the periodic table. So, following the 288 rule, or the way I taught you in grade 11, counting the squares, in our first period on the periodic table there are 2 squares, and in the first ring there are 2 electrons. continuing to point at each square separately until I'm pointing at aluminum. I've gone 1, 2, lithium is at number 3, and beryllium are both in ring 2. And then there's a space that I respect, and then there is 1, 2, 3, 4, 5, 6 more. So I put 6 more electrons still in ring 2. Again, as I taught you in grade 11, it's important to separate those electrons and respect that space, and we're about to see why in just a few minutes. We're still not counting up to aluminum, so we continue to count. Ring 3 is period 3, so 1, 2 before the space, and then there's the big space, and then I need 1 more after the space to make aluminum. As expected, 2 plus 2 plus 2 plus 6 plus 1 adds up to 13 electrons. And as expected, there are 3 electrons in the outer shell. Let's do another example together. This time, let's pick bromine. I want to pick an example where we go past the transition elements. So again, to draw bromine, I start by putting the symbol Br for bromine, and I need to know how many rings I need. I figure out how many rings I need by figuring out which period bromine's in. Numbering my periods, this is period 1, there's only 2 squares in it, 2, 3, 4. I see that bromine is in the 4th period, so I will draw 4 rings for bromine. Bromine is in family number 7. Family, so go vertically, 2, 3, 4, 5, 6, 7, 8. Because of that, there will be 7 electrons in bromine's outer shell. I also know that I will have a total of 35 electrons because we're at atomic number 35. So counting each square in order until I get to bromine. In period 1, there are 2 squares, so I put 2 electrons. Period 2 has 2 before the break, and then there's a big space, and then there's 6 after. Period 3 has 2 before the break, and then there's a space, and then there's 6 after. Period 4 has 2 of them in the numbered columns. The next 10, as we count through the transition elements, always will go back 1 level. So those next 10 electrons back up into the 3rd ring, but only for when we count transition metals. Jumping back into the regular representative elements, you'll see that I count 1, 2, 3, 4, 5 more squares, and so I put 5 more electrons. We now have a total of 35 electrons, and as expected, 7 in the valence shell. So it's important that when we're drawing these, we remember when we count those electrons to back them up 1 level. When we count the electrons corresponding to the lanthanide and actinide series, which fit here, you'll back these guys up 2 levels. The periodic table that comes with my smart software is not designed for doing Bohr diagrams and electron configurations, but the one that I hand out to you with your work packages is. The difference in some of the varieties in periodic tables often is where we branch down to form the lanthanide and actinide series. So if you use the one that I have in class and follow in order with these same rules, you will always get them right. If you need more practice in drawing Bohr structures, watch my grade 11 video on drawing Bohr diagrams. Okay, now that we've talked about Bohr diagrams, I want to go back to quantum theory because in many ways they are very, very similar. First of all, why are we calling it quantum theory? Well, a quantum is a fixed amount of energy. It's a package of energy. A quanta would be multiple packages, so quantum is a singular. How much energy is it? Well, it's enough energy to kick an electron from one energy level to the next. Suppose I have an electron floating around my nucleus in the 1st ring, and I want to kick it up an energy level. Imagine that you're holding a pencil in your hand, and your other hand is hovering above it, and you want to catch the pencil in your bottom hand with your top hand. You have to put energy to throw the pencil up so that your top hand can catch it. The amount of energy that you use to push it up is one quantum. The amount of energy that it takes to kick an electron up to a ring further away from the nucleus is a quantum. Remember, electrons have negative charge. They were attracted to the positive nucleus, so to push them away takes work. What happens, though, when you take the energy away? If you use the pen in your hand analogy, you're now holding a pen in your top hand, and your bottom hand is empty below it. Well, if you open your hand, the pen falls. Once I stop pushing on the electron falls back down to the ring it was belonging to. The ring that electron would normally be found in is called its ground state. When we draw Bohr diagrams and we put the electrons on, we're putting them in a position we'd expect to find them. The reason that we expect to find them is that's the lowest possible energy position for that particular electron. So when an electron falls from its higher energy level, we call that an excited state, down to its normal energy level, its ground state, the energy has to be released. Often we find that energy gets released in a package of light called a photon. So that energy that gets released in the form of a photon. And photons have specific amounts of energy that corresponds with specific wavelength. Now, when we think about hydrogen, hydrogen's ground state is to have one electron in its first ring. That's where we'd expect to find it. It is possible, if I hit hydrogen with enough energy, that I can kick this electron up to the second ring. When that electron falls back down again, it will release energy, and it will release it as a wavelength, as a package of energy in the form of a wavelength that corresponds to a color of light. In this diagram, we have it marked as green. It is also possible that I could have really kicked this electron hard and kicked it up to the third energy level. Remember, just because these rings are empty doesn't mean they don't exist. When that electron falls, it might fall just one energy level before it gets kicked up by energy again, or it might fall 2 energy levels. The amount that it falls, the energy that it falls, will always correspond to one full wavelength. And the reason for that is, if you could imagine if you're going up a ladder and you miss a step. Your foot can't stop halfway down. We know that that's not possible. If you've ever slipped a step on the ladder and you accidentally miss the rung, it seems to come down hard. It doesn't make sense. It'll continue to fall until it hits a rung. It's the same with energy. We have to have one complete wavelength in order for the energy to be released in a full package. Each of those wavelengths corresponds with a certain color. And when Bohr looked at hydrogen, and he looked at it through a prism, rather than seeing a complete rainbow, he got a spectral pattern. He saw a series of colored bars, and this is what led him to his idea that there must be specific rings. So we have a bunch of words on this page. We are working with Bohr's idea of the rings, and you can think about rungs on a ladder. And we know that to kick up to the next ring is called, the amount of energy is called a quantum, and when that energy is released, it comes out as a package of light called a photon. All right. Now, here's where we're going to take a couple of different names to things you already know. When we are talking about chemists who talk about quantum theory, I think sometimes they like to change the wording just so they sound smart. So remember when we drew the Bohr diagrams and we talked about ring 1 and ring 2 and ring 3 on our Bohr diagram? Well, now we're going to call those principal energy levels. So our ring is now called a principal energy level. Doesn't that sound so much more sciencey? But each principal energy level now has been designated by giving it a number. Because, you know, as chemists, we're lazy. We don't want to write out big, long words, even though we love to say them. So Ring 1, which was period 1 on the periodic table, had 1 energy level. They decided to number it 1. Ring 2, elements found in ring 2, lithium, beryllium, boron all the way through neon, put their electrons into the second ring on their valence shell. We now call that principal energy level 2. We gave it a number, we called it 2. Ring 3 we call 3. Ring 4 is principal energy level 4. Starting to see the pattern? It's not really anything more difficult, it's just we've changed the words. But here's where there's a little bit of a deviation, because each ring gets fatter. And as they get fatter, we can divide them into sublevels. Ring 1 has 1 sublevel, and we've named that sublevel S. Ring 2 is quite a bit fatter. It has 2 sublevels. We call the first one S and the second one P. Ring 3 is even fatter. It has 3 sublevels, S, P, and D. Ring 4 would have 4, S, P, D, and F. Ring 5 would have 5, S, P, D, F, and they've reserved a name for the 5th one, G. Ring 6 has 6. Ring 7 has 7. What does that look like? So picture this scenario where we have our nucleus off to the left in black. Ring 1, which we now call principal energy level 1, is this fixed distance of space from the nucleus. And because it's reasonably small, it only has 1 sublevel that we name S. We'll call it 1s. Ring 2, we now call principal energy level 2, is quite a bit fatter. So we can divide this up into 2 sublevels. It's like trying to take a step, but it got too big, so we built a half step in between. We call the first one 2s, and the second one 2p. Ring 3 is fatter still. So this would be a really big step on a ladder. So we're going to build 3 sublevels, 3 sort of little partial steps. The first one is called S, always S. The next one is called P. The third one is called D. Ring 4 would be fatter still. In the 4th ring, because it was so fat, you'd be able to cut it up to be 4s, 4p, 4d, and 4f. So we're starting to not think about the electron as a bead on a piece of yarn, but almost as existing within an area of space. And now we're going to say, well, I know any electron found in the second ring, the second energy level, could be in this huge area, and so we've narrowed it down to, is it the closer to the nucleus part or the further from the nucleus part? The interesting thing with the S, P, and D sublevels is they actually have spaces that are big enough within them to hold only 2 electrons at a time. And those spaces are called orbitals. We're going to come back to orbitals later. I just want to introduce it to you now. And the orbitals have very specific shapes. For example, electrons found in the S sublevel always form a spherical or sphere-shaped orbital. It would look kind of like this, like a rubber ball. The ones found in the P sublevels actually look like 3 party balloons tied together. You'd have a party balloon on an x-axis and a y-axis, if you think about 2 party balloons, and then as best as I can draw, you'd have one on a z-axis coming in and out of the page. We're not going to worry about the orbitals or the shapes of them at this moment. Right now, I'm worried about when we talk about where electrons are, we're changing the name from the ring to the principal energy level, and we know that as they get fatter, we can divide them into sublevels. Now, when we go to put electrons into each of those different sublevels, you'll very often see this wonderful little diagram accompanied by a name called the Offbar Rule. Offbar is a German word that means the rules of order. So the Offbar for building a house might be that you start with the basement and then build the walls and finally the roof. You always start with the lowest energy and then proceed up to the higher energy. It's the same with electrons. Now, very often you're going to have teachers say, memorize this picture, which I think translates to, find a place to write it on the back of your hand and hope no one sees it. We don't have to memorize, because when the periodic table was made, without understanding about electrons or energies or any of this modern idea, it arranged itself perfectly according to the Offbar Rule. We're going to go back to the pages where I drew the electron configurations for our two elements and show you how, instead of doing it as a Bohr diagram, we could draw this using quantum theory's description and make it an electron configuration. All right, here is the drawing that we did for aluminum. This is a Bohr diagram, and they do take up a fair amount of space on the page. Electron configurations are more of a sentence that describes where each electron is. Using the same count and point version that we used before, if I are going to count my squares until I get to aluminum, you notice that in the first period I'd count 2 squares just like we did, and we put 2 here. We now call the first period principal constant number 1, so I'm going to put a big 1. And I know that that first level has one sublevel named S, and I could see that there are 2 electrons in it, 1s2. That allows me to count hydrogen and helium. Following the numbering, number 3 is here, and we call that ring 2. Remember how I said ring 2 is 2 sublevels? We have 2s and 2p. Well, these first 2 squares before the break hold 2 electrons. After the break, we hit a series of 6 squares to hold a total of 6 electrons. Notice how my second ring had 2 sublevels. Continuing on, I've now pointed all the way to neon. Number 11 and 12 are principal energy level 3. We always start with an S, and I've got 2 electrons. And then aluminum would be principal energy level 3 still, but we only need 1 more. 2 electrons in 3s and 1 in 3p. So this was my 1s with 2 electrons. 2s had 2 electrons. 2p had 6. 3s had 2 electrons, and 3p had 1. What I've written here is called an electron configuration. Electron configurations take up a lot less space on our page and tell us where we will find the electrons in relation to their position on the periodic table. Perhaps you have noticed that any time I counted the squares in these first 2 families, they always went into an S sublevel. Anytime I counted electrons corresponding to this row of 6, they went into a P sublevel. S sublevels can always hold a maximum of 2 electrons, and P sublevels hold a maximum of 6 electrons. Let's try doing the electron configuration for bromine. I'm going to do this by counting the squares, and you'll see how it correlates with the Bohr diagram above. We don't need to draw a Bohr diagram first. Holding onto the periodic table and counting the numbers in order until I get to bromine. 1 and 2 are in sublevel energy level 1, which has 1 sublevel named S, and there are 2. Energy level 2, sublevel S, there are 2 squares. Going across to number 5, we're still in the second period, so we're still in energy level 2, but this is sublevel P, and there are 6 electrons. We're still only counting at number 10. We got to get to 35. Numbers 11 and 12 are in energy level 3, sublevel S. There are 2 electrons. Still energy level 3. This is sublevel P. There are 6 electrons. This has taken us up to number 18. We got to keep going. Energy level 4 has 19 and 20. This section of 10 electrons always backed up one level. Remember them? So this goes back into energy level 3. We call this sublevel in the middle D, and there was a total of 10 electrons. Then we went back into regular energy level 4, sublevel P for 5. Remember, I told you earlier that the first energy level has one sublevel. The second energy level has two sublevels, an S and a P. The third energy level has 3, an S, a P, and a D. So even though we see that the fourth energy level, my fourth ring, has these 2 electrons being further out than the 10, so they're further from the nucleus, because they were listed before those 10, they are going to be lower in energy. The reason for this is, when we had filled 8 electrons, when we had filled the initial 8 electrons into the third ring, it was reasonably stable. It was slightly easier to add another ring and put 2 electrons even further from the nucleus than it was to take a stable ring and backfill, shove 10 more electrons in, but only slightly. The next easiest thing to do was to go back to that fourth ring for the remaining electrons. So the nice thing about an electron configuration is that we can see the energy associated with each electron. The lowest energy are the first ones that we would do. The highest energy is the last one. So the lowest energy electron was the 1s for 2, and our highest energy electrons were the 5 in the 4p sublevel. I want to do one more example with you. So let's pick something interesting to go through. Let's try picking tin. Tin is found here, SN number 50. It would take a whole lot of rings to do this as a Bohr structure. We're not even going to try. We're going to point at each square in order and describe it in terms of its electron configuration. So starting at number 1, hydrogen and helium, we have energy level 1, sublevel S. There are 2 squares, so 2 electrons. Lithium and beryllium are in energy level 2, sublevel S, 2 electrons. Boron, all the way through neon, is still energy level 2, sublevel P for 6. Keep going in order. If you're not sure about the order, the numbering tells you the answer. Numbers 11 and 12 is energy level 3. We're in sublevel S for 2. Still at energy level 3. Remember, this square over here is the P sublevels. We have a total of 6. Calcium and potassium are energy level 4, sublevel S for 2. Now remember, these guys here backed up one level. There was a total of 10 of them. So we're back into energy level 3. We call these middle guys the D sublevel for 10. Going back into ring 4, energy level 4. This middle section is the P sublevel for 6. We're still not at 10. So I go to energy level 5 for 2. Backing up one level as I count my transition ones. So this, instead of 5, is 4, D for 10. And then back into my regular energy level 4, sublevel P, and there are 2. This is the electron configuration for tin. Now I'm going to show you a shortcut. There is a noble gas shortcut, and that says, hey, go to the last noble gas you passed on the way here. So if I back up, now if I back up until I reach the last noble gas I passed was krypton. So I'm going to say after krypton, everything up until krypton was completely full. Those were inner shells. There was nothing I could do really as a chemist in terms of using them. I know as a chemist that I use my valence or outer electron. So after krypton, you'll see that I filled in my 5th ring, 5, S for 2, and then 4D for 10, and then 5P. Oops, I had that wrong up here. Fix that now. 5P for 2. So after krypton, this is how we filled in the outermost shells. So this is the shorthand for tin. You're welcome to use the shorthand for anything that you would like. I'll do one more example for you. For this last example, we'll do barium. Barium exists at number 58. And so it is way, or 56, sorry, it is way down on there. It would take us 6 rings to draw a Bohr diagram. It would be a long, hard slog to draw all of the electron configuration. But the last noble gas that I get to before barium would be xenon. So for barium, I could say after xenon, which would be full up, I need to add 6 because I'm in the 6th period. This is sublevel S for 2 electrons. Now that's a pretty easy thing to do. So how can I label my periodic table in order to make my electron configurations easier? Remember to number your periods starting at hydrogen. There are 7 periods. Remind yourself that when you get to the transition elements, they bump back 1 level. So electrons counting here is 3, 4, 5, 6. And on your periodic tables that I gave you, which is slightly different, remember also on your periodic tables, lanthanum and actinium come down here. They belong here, and for these guys, you bump them back 2 levels. So after 6, this would be energy level 4 and 5. After you get to the end of 4, then you come back to ring 5, energy level 5 up to here. Remember, passing my transition metals, we go back to my regular numbered periods on the periodic table. So with a little bit of practice, you'll find that the electron configurations are a lot easier for you to draw. There's lots of practice for you to do this if you start reading chapters 5.2 in your textbook, and then when you're done, you can start on questions 15 through 20 on pages 146 to 155.